Location pooling. I will explain location pooling on the following example. Consider a supply chain where there is a single distribution center and a number of territories that, where the distribution center delivers the product to the territories, and then in the territories there are sales reps, each serving the demand in that territory. So this is an example similar to the one we had in the order up to model in topic 5, where we had Medtronic's in-sync pacemakers, right? There was one distribution center delivering to a large number of territories. Each territory was served by one sales representative who would deliver for the demand in that territory. So here we have an example of just 3 territories with 3 inventory stockpiles, right? This is the case. Each of the territories has one sales rep, and there is one inventory, separate inventory in each territory. And the lead time is 1 day from the distribution center to territory. Now consider a location pooling strategy would be, right? The location pooling strategy would be the 3 territories now become equivalent to 1. So they have one inventory stockpile, and then each sales rep, maybe we still keep the 3 sales reps, they have to get their units to satisfy the demand in their territory from this single inventory. Assume the inventory is automatically replenished and the lead time from the DC to that inventory is still 1 day. If we evaluate the inventory with different number of pooled territories using the order up to model, that was the topic considered in topic 5, we can find out the following. So assuming that each territory is identical with expected demand 0.29 with Poisson distribution, assume required in-stock probability in each territory is 99.9%, and assume in all cases lead time is 1 day, whether it's individual or pooled territories. So here we have evaluation. The first one is, of course, equivalent to what we had in topic 5 on order up to model, right? That where we determined for that kind of service level, we need 4 units order up to level, and then we can evaluate the amount of end of period inventory and the pipeline inventory. So end of period inventory for that level is 3.42 units, but we can also convert it to days of demand, right? So measure it in this inventory in terms of the number of days that this inventory should be sufficient to cover demand, right? So this is basically 342 divided by 0.29. In the second line, you see 2 pooled territories, and of course the demand in 2 pooled territories will be twice as large, right? So 2 times 0.29. The order up to level that is sufficient for the same 99.9% in stock probability is actually higher. It's 6 units now, but it's not 2 times higher, notice. And also the expected end of period inventory is right on hand inventory is 4.84. It is much less than 2 times this, right? And if you measure it again in days of demand that this can cover, right? So we have to divide it by 2 times 0.29. So we have to divide it by this value, right? And so that gives us 8 days, 8.34 days of demand. In the terms of pipeline, nothing changes because if the daily demand is now twice as much and we have lead time 1 day, the lead time, the on pipeline inventory is just average demand times lead time, so it is still 0.58. And in terms of days of demand, right, dividing this by the daily demand, it's going to be 1. And actually notice it will be always 1. So pipeline inventory is not affected. But as we increase the number of pooled territories, you see that the end of period inventory, even though it is increasing slower than the demand, and therefore in terms of days of demand that it covers, it is actually decreasing. So we see, right, that if you consider, for example, 3 territories, the end of period inventory is not 3 times 3.42, it's 5. It is much less than 3 times this, right? And if we measure it in days of demand, you can see that decrease, that it is significant. And so we see that pooling, first of all, reduces expected inventory for the same service level. All those cases are with 99.9% in stock probability, right? But of course, we can, in fact, keep the same amount of inventory. So, for example, in 3 territories, we could keep order up to level, let's say, 3 times 4, 12, and have the same kind of end of period inventory, right? But we could at the same time increase the service level. So, if we had maybe a lower probability of in stock, if we pool inventories, we can keep the same levels of inventory and increase the probability of being in stock. This is actually hard to increase because it's already so close to 100%. And of course, we notice that the impact on pipeline inventory is null. So there is no impact here. Why does location pooling work? Well, it works for the same reason for which having larger lifeboats on a cruise ship reduces the cost of those lifeboats. It works, both of them work because the pooled demands have smaller coefficient of variation compared to coefficient of variation of a single demand, right? So we see that in order, in this case, to satisfy the same service level, to provide inventory with the same in-stock probability, we need less and less inventory because coefficient of variation is dropping. So on this chart, you see the green line, which is showing you the coefficient of variation when we go from 1 to 2 to 3 and so on, pooled inventories or pooled territories in this case. And you also see the plot of the numbers that we saw in the table just a moment ago, the end of period expected inventory measured in days of demand. So somehow is normalized for the number of territories. You see that, right, the per territory inventory level will actually be dropping significantly. And notice these declines have smaller and smaller slope, right, as we pool territories. So the most benefit you capture by pooling only a few territories and then pooling them further gives you much less benefit, at least per compared to the scale of pooling, right? So the benefit is really highest for the smallest, for the first pooled inventories.